Hi everybody, this is going to be our note for 2.3, velocity, acceleration, and second derivatives. So I know I mentioned in class before that calculus and physics are related, and we're going to start seeing that here in this lesson. So let's get right into it. So up until this point, we have understood that differentiating and finding the derivative represents the rate of change for a function. This lesson has us taking a cross-curricular approach. We will be applying our concepts to physics. However, before we do that, we need to understand one more idea for derivatives. Well, like one more for today, because there's definitely going to be more about derivatives. But one more idea for derivatives for today. So there's something called higher order derivatives. And if we have this function f at x that we're used to seeing, well, I'm going to show you some more math jargon. Here we go. The first derivative of f, or f prime, is what we see here. F prime is equal to y prime. And then in this notation, we see it like this. We can also have a second derivative. So the second derivative of the function f, or f double prime, is this. And then the third derivative, triple prime, is this, and so on. And the longer this goes, we just say n, where n could be 5, 6, 7, 8, 9. But we call this super when we get beyond 3. Now we're not going to see a lot of super 4, super 5, or a lot beyond that. We're going to see f prime, obviously, f double prime, and f triple prime. We'll see these ones the most, and maybe a little bit of this, but mainly just these three. But you should be aware of how to know all these and how to find all of these as well. So let's take a look at this notation here, because it looks very confusing, but I assure you it's, if we break it apart, it's actually not too bad. So we have our function f at x that we have. And our definition for f prime, or just the first derivative, is just f prime at x, which we already know. If I want to find f double prime, or the second derivative, f double prime x, well, this is really just the derivative of f prime at x. So just the derivative of that derivative. If I want to find f triple prime, or the third derivative, well, there's my notation. I have kind of three apostrophes here. Well, it's just the derivative of the second derivative. And super 4 is just the derivative of the third derivative. So we can just keep taking the derivative again and again, n number of times. So n could be 6, 7, 8, and so on. So this looks, again, complicated, but we can just summarize this in a sentence that I'm going to put right here. So all this means is we can take more than one derivative. If I'm taking derivative of a derivative, because we can do that, and we're going to practice that in just a second. But if I'm taking a derivative of a derivative, I follow the same steps that we already know about taking the derivative. So any of those laws that we learned, or rules, and any of the stuff we learned in 2.2 as well. So I just follow the same rules and the same steps if I'm taking the derivative more than once. Sorry, I just wanted to straighten out the camera, so sorry for that cut. So let's do an example. We're going to find the first derivative, second derivative, third, fourth, and fifth derivative for this function here. So if you want to try this on your own, you can. I'll be doing it down here. If you want to pause the video, and then you can kind of check with what I did afterwards. So we're going to just write my function again. F at x is equal to negative x to the power of 4 plus 3x squared minus x plus 1. Then I'm going to find the derivative of that, the first derivative. So I'm using my derivative rules here. Then I want to find the second derivative. Double prime here. Just find the derivative again. and then again, and we can just keep doing this as many times as we need to, or until I just can't take the derivative anymore. And there we go. Note for the super 4, super 5, and so on, we should put the number in brackets but as like a superscript, like raised above the number. So kind of like an exponent, but in terms of this function notation, we just treat this as the fourth derivative. So we can just take this derivative over and over and over again, and that's kind of a good chunk of our lesson. But now we're going to start applying this to different scenarios. Okay, our next example, determine the second derivative at x equals 2 for the function f at x is equal to this. So I'm going to just rewrite my function again. And if you want to pause the video, try it on your own, and then unpause it, and I'll be taking it up. So find the first derivative. I move the exponent to the front here, according to my derivative rules. 3 times a third just becomes 1, so that's why it becomes 1 there. So that's the first derivative. I'll find the second derivative now. I get 2x minus 2, and we want it for x equals 2. And there we go. So as long as you know the derivative rules, you can just do the derivative more than once if you need to. So now we're going to get to the actual physics portion. If you have taken physics, this might be a little bit of a review for you. And if you haven't taken physics, that's okay, because you're going to learn about these things now. So before we get started about learning about physics, we have to learn a few key terms. So first we have to learn about speed, and we have to learn about velocity, because they are slightly different from each other. I mean, they might sound the same, but they're slightly different in terms of, especially in terms of our physics definitions. So speed is what we call a scalar quantity. It describes the magnitude of motion, but does not describe a direction. Magnitude just means like a number. It has a value for some sort of motion. So like, as an example here, a car travels 100 kilometers per hour. Notice so there's a number here. The magnitude of motion is 100 kilometers per hour. That's how fast the car is. But there's no direction. We don't know if the car is going north, south, east, west. So we just say it's just their speed. So it's just the number, a scalar quantity. Velocity is what we call a vector quantity. And we're going to get all into vectors a little bit later. But a vector quantity has a magnitude and a direction. So the answer in a velocity question will be either positive or negative for our case, which indicates direction. Sometimes positive will be north, negative will be south, or just forwards and backwards, or whatever. But we will have a direction, and the positive negative will help us decide that direction. So some more key terms we're going to have to learn. We're going to have to learn about displacement. Displacement is the distance an object has moved from the origin over a period of time. So we might see this as different functions as like s at t. We might see it as h at t if we're talking about like height. And d at t is what we see a lot of, just distance or displacement over time. We'll probably see this in meters, kilometers, any just unit of measurement. And some notes. When s at t is equal to 0, the item is at a starting point. When s at t is greater than 0, meaning a positive number, the item is on the positive side or above ground. And when s at t is less than 0, the item is on the negative side or below ground. So displacement and distance can kind of seem like the same thing, but again, they're kind of different, like speed and velocity, where distance just worries about the actual number or measurement of the distance between 2 points. Let's say like 100 meters here. Not drawn to scale, obviously. But displacement talks about how an object has moved from one place, let's say an origin, over a period of time. So if we have like a starting place here, how has this object or person or item moved from its starting position to another spot or another point? What's important is not only their distance from that starting point, but also their direction from that starting point. Because if we're talking about distance and displacement here, I mean, if we're talking about this from starting point to end point, well, this distance might be the same as it was for all of these, but the person's or item or object is in a completely different location. So they've been displaced somewhere, maybe 100 meters, but maybe like southeast of where they were originally. Okay, to summarize, so distance is just the measurement, or the measurement between these 2 points, while displacement is the location an object has moved in relation to where it started from. So the distance is taken into account, but also the direction from where that object has started from. So velocity is the rate of change of the displacement within with respect to time. So we can say that the velocity is really just the derivative of the displacement function. So if I take the derivative of this, I get the velocity. Our units are meters per second, kilometers per hour, anything relating to speed. When v at t is equal to 0, the item is at rest, or might be changing directions. If v at t is positive, the item moves in a positive direction, and if v at t is negative, the item moves in a negative direction. Lastly, we have acceleration. It's the rate of change of velocity with respect to time. So my acceleration, we often write as at here, is really just the derivative of velocity, which is really also the double derivative of displacement, which we could also write with an S. That's why we have to learn about double derivatives and triple derivatives, because this is an example where we do see if I take the derivative of a displacement equation, derivative of that gives me velocity, double derivative gives me acceleration. So let's start doing some application with this. So our first example is a construction worker accidentally drops a hammer from a height of 90 meters while working on the roof of a new apartment building. The height, s in meters, of the hammer after t seconds can be modeled by the function this, where t is greater than or equal to 0. So determine the average velocity of the hammer between 1 second and 4 seconds. So this is really average velocity. This is kind of an average rate of change. Let's say average velocity, just the rate of change between these times. So s at 4 minus s at 1 all over 4 minus 1. Again, this is just our slope equation that we did in chapter 1 and that you learn in advanced functions. So I'm just going to put my this function at s at 4, subtract this function s at 1, and then we're doing it 4 minus 1 seconds. So I'm going to just write that in my equation here. I'm going to have 90 minus 4.9 4 squared minus 90 minus 4.9 1 squared all over, we can subtract that to get 3. Then I can work this all out if I want to. So I worked this all out and I got negative 73.5 over 3, which gives me negative 24.5. I didn't want to show all the steps for this. I don't have a lot of room, and this would be a very long note otherwise. So if you must remember, though, I should put brackets around this to do this first, and brackets around this. This plays an important part with the negative here to make sure we're distributing that into the brackets when we after we solve. So we get this as our answer. So this is the average velocity between 1 second and 4 seconds. explain the significance of the sign of your result in part A. So the sign is negative. So we learned for velocity, velocity is less than 0, the item moves in a negative direction. So our velocity is negative 24.5 meters per second. The negative represents the object falling. You can see it's like it's going downwards. So it's going down in the negative direction. That's why we have a negative velocity. Now it says determine the velocity of the hammer at 1 second and at 4 seconds. So now we're drawing the instantaneous rate of change at this time and this time. But now we have our new method of finding the derivative. So we don't have to use first principles anymore, where it takes a very long time. So if I know my equation, S at t is equal to this equation, 90 minus 4.9 t squared. Well, if I find the derivative of that, S at t, which is also the velocity, I will get negative 9.8 t. So I can determine the velocity now based on this equation at these times just by incorporating them into t here. So I'll have v at 1, v at t is equal to this, and then v1, we're going to get negative 9.8 meters per second, so that's the speed at this time, and I'll do it for 4 seconds, and I get negative 39, oops, wrote that completely backwards, 39.2 meters per second. So we've been doing these kind of questions, I think, since grade 10. This is really just quadratic here. We've learned some new things along the way, but some of these questions are still the same as they were in grade 10. So when will the hammer hit the ground? Well, if our equation is measuring the height off the ground, and we have S at t is equal to 90 minus 4.9 t squared. Well, the hammer hits the ground when the height is at 0. So if I set the height to 0 and I solve for t, well, that'll be the time where the height is at 0. So I'm going to start isolating for that. I'm going to get 4.9 t squared is equal to 90. Just moving this over. I get t squared is equal to 90 over 0.9. Just divided both sides by this. I get t squared is equal to 18.367. I then square root both sides. And then I get t is equal to, positive or negative because I'm taking a square root, 4.286. So we have t is equal to negative 4.286 and t is equal to positive 4.286. So which time is it going to be? Well, we do have a restriction, they tell us, that t, or the time, has to be greater than or equal to 0. So I cannot use this one because that's a negative value. So the hammer hits the ground at 4.286 seconds. So we'll say, therefore, this number. Determine the impact velocity of the hammer. So you're probably wondering, well, what is impact velocity? So if we have this item hitting the ground, well, we just want to know when the item hits the ground, what is the velocity when it gets there? I guess I didn't really need a diagram. So what is the velocity when it hits the ground? So we know it hits the ground at let's say 4.3 seconds. So then all I really want to do is find the velocity which we have the velocity equation to be negative 9.8t. Well, what is it at time 4.3 when the hammer hits the ground? So we get the answer of negative 42.14 meters per second. So again, we have a negative value. We can say, therefore, impact velocity is negative 42.14 meters per second. Or you could just put a positive value, 42.14 meters per second, and then assign a direction, down. Because a negative means downward, so if you write it like that, you can make this positive, but make sure you incorporate the direction, which is downwards. It says, determine the acceleration function. What do you notice? Interpret it for this situation. So if my velocity is equal to negative 9.8t, we said that the acceleration equation is just equal to the derivative of the velocity equation. So if I find the derivative of this, I will get the acceleration. So this gives me just negative 9.8. So what is this number? If you've taken physics, you probably know. If not, well, we have an acceleration. This is a rounded number as well, of negative 9.8 meters per second squared. That's our unit for acceleration. I think I forgot to add that in the note. I will add that afterwards. I will just do it right now. Meters per second squared. And what is this acceleration? Well, this is also the acceleration of gravity. So in this question, we're going to be examining the graphs of distance, velocity, and acceleration graphs and see how parts of these graphs are connected to each other. So I tried to line them up as best as I could on your handout, so hopefully that'll be very clear for you to see. So we have the position of a particle moving along a straight line can be modeled by the function this, where distance s is in meters, time t is in seconds, and t has to be greater than or equal to 0. So a graph of the position function is given. Sketch graphs of the velocity and acceleration functions. Determine when the particle is speeding up and when it is slowing down. How does this relate to the slope of the position function? So you're going to notice a few things. One, I gave you all the graphs. That's because I didn't want to draw it and then we're going to draw it maybe a little bit differently or not to the same spot. So I put all the graphs in just so we can line up and see how the different graphs are going to interact with each other. Secondly, what kind of function do we have that we learned from advanced functions in grade 11, hopefully, that we have a cubic function. And this is kind of what a cubic function can look like. So I'm just going to put some numbers in the graph. I'm just going to put these large lines here are going to be 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to do that for all of the graphs. So that way they can line up and we can see what's happening at these particular seconds. And I'll do it for the same here. 2, 3, 5, 6, 7, 8. So you don't need, no, I just labeled this the same way. So sorry I didn't show that in the video. So we're going to first look at some important points. I want you to note, where do we have slopes of 0 that are kind of easy to spot? Where will we have a slope of 0? Well, slope of 0 means we have a horizontal line. So I want to find at what points will I find that the slope of a tangent line will be 0? Well, I can see at this point and here at these max and min values. If I find the slope of the tangent lines at these max and min values, we're going to have a slope of 0. So we can see here we have at t equals 2, we have a slope of 0, and at t equals 6, we have a slope of 0. So now going back to advanced functions, I'd like you to tell me, where do we have areas of increase and where do we have areas of decrease? So I can see from here to here, yes, I made a typo. I had to get another piece of paper, so that's why the numbers aren't here anymore. So I see that it's increasing from here going up to here. So we can say when t is greater than or equal to 0, but less than or equal to 2, we have s at t is increasing. You're probably wondering, why do we need to know that, where it's increasing and decreasing? Well, we'll see in a second. Where is it also increasing? Well, up until this point, on this side, when t is greater than or equal to 6, but less than or equal to 8, s at t is increasing again. So at these intervals, and up to here, our function is increasing. And now in between that, when t is greater than or equal to 2, but less than or equal to 6, well, we have s at t, well, s at t is decreasing. So let's find the derivative of this to get our velocity equation before we start examining what's happening here. So taking the derivative of this, I'm going to get 3t squared minus 24t plus 36. Now it's quadratic, I get this parabola here. And if we were to actually join up these times at 2, well, we said at 2 we have a slope of 0. So what does that mean in terms of our velocity here? Well, notice that when I have a slope of 0 at this time, we're going to have this. So my slope of 0, I also have in my velocity equation an x-intercept. And this also happens at 6, where we have a slope of 0. It also lines up with an x-intercept on our velocity equation. So what we can say is, when our displacement slope equals 0, so when the slope on a displacement graph is 0 slope here, our velocity is 0. Also notice when our displacement is increasing, so when our displacement increases, we can see that the velocity is, we'll notice from here to here, our graph is increasing for displacement. And what do we notice about it on our velocity graph? Well, from here to here, it's still in the positive section on the graph. And then it gets to 0, where it gets to our slope of 0. And then afterwards, when our displacement graph starts increasing again, well, then my graph for velocity is also increasing. So when our displacement increases, velocity is positive, meaning above the x-axis. So above y equals 0. And this happens in these two intervals. So when 0 is less than or greater, or sorry, less than or equal to t, this, and for this. And then we also notice when our function is decreasing here, well, that's when our graph is in the negative. So when displacement decreases, velocity is negative. below y equals 0. And then this happens at that interval when t is greater than or equal to 2 but less than or equal to 6. So that's just something we can see between these two graphs. Lastly, we can find the acceleration equation, or the double derivative of s at t. So I could do the derivative of this twice, but since I took the derivative once, if I take the derivative of this, I'll get the derivative of that. So I'm going to get 6t minus 24, which looks like this. As a graph, it's a linear equation, so we're going to have a straight line. I'd have a y-intercept at negative 24, which is down here. But what can we notice here? Well, same kind of idea where my slope in my velocity graph, my slope at the vertex is 0. And that also lines up with where our acceleration graph lines up at 0, which is right here. So we can say now, when slope of v at t is equal to 0, which this occurs at, this occurs at t equals 4 on our graph. Acceleration equals 0. And very similar that we saw up here, that when we had this increasing, this was in the positive part. Well, we see in our velocity graph that this is decreasing from 0 to 4, and then increasing from 4 and onwards. And we do see that here as well. So when velocity decreases, and this happens between 0 and 4, and this happens on our velocity graph. When this is decreasing, the acceleration is negative. And when our velocity graph was increasing, our acceleration became positive. So when velocity increases, acceleration is positive. So just some patterns we can see between these graphs when I'm doing first, second, and third derivatives. This one might take a bit of studying, or if you try the homework for this, it'll be good practice just to kind of see how these are related, but these are the main things we have to remember as I take the derivative in terms of these graphs. So I know there's no homework at the bottom. I will put the homework here. It's page 106 to 109, 1 to 2 if you just want to do A, C, E, so on. Try 3 to 5, and 7 to 12. And if you want to do more than that, go for it. If you think I get this sign, I can skip a couple, do that as well. But that's it for the lesson, and thanks for your time.